In our last lesson, we've seen how Heisenberg's uncertainty principle has showed that we had to move away from a model where we thought of electrons as being in specific areas, so specific energy levels, to a model where we can't quite say that electrons are definitely in one area or another, but we talk about the probability of finding an electron in a certain area. So what does this really look like? Well, if we were to draw the nucleus of an atom, we'll draw it there, and then with a red dot, we're going to show you the probability of finding an electron in a certain area. So say we've got an electron and it's in the ground state. What this really means here, according to Heisenberg, is that it will be somewhere around the nucleus. And it was actually a scientist called Erwin Schrödinger. Okay, so Erwin Schrödinger, spell this right, S-C-H-R-O-D-I-N-G-E-R, Erwin Schrödinger, who wrote some very complicated maths equations and solved them to basically describe where we can find these electrons. Okay, so what did Schrödinger do? He wrote some very complicated maths equations. We don't really need to know anything about them, but they basically described where we can really find electrons. So with a red dot, we're going to kind of look at that idea. So let's say, for example, we were to take like thousands of snapshots of an electron moving around a nucleus. The idea here is that, well, we might find it here. We might find it here, here. In the next picture, it might be here, 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 here. Okay, so I'm going to keep drawing the location of the electron. Remember what Heisenberg said, sometimes just by chance, it might be over here. Okay. There, the very odd time, it's not where you expect to find it. But the average position, it turns out, would be in this circle area, if you like, or this spherical area around the nucleus. It's not always in an exact location that you can find it. The very odd time, it will be in a different location, just by chance. But the vast majority of the time, we find it in this area around the nucleus. So all of these are different pictures of the electron at different times as it moves around. So remember, this is just a thought experiment, but this is kind of illustrating the idea. So we say that actually this zone here that I'm going to circle in black, this shows us an area where there is a high probability of finding this electron. Why do we talk about probabilities? Well, it's not definitely there. Sometimes it's out here. Sometimes it's here, sometimes it's here, and sometimes it's here. But it's very rare. A high probability is that it's going to be inside the black circle. This is an area around the nucleus where there's a high probability that we will find an electron. And this is what Schrödinger's equation showed. It showed the probability of finding an electron in different areas. And that's what became known as what you see in red here. We call this an orbital. So this here in black is an orbital. What is an orbital? It's an area where there's it's a region in space around a nucleus where there is a high probability of finding electrons. Most likely we're going to find them there. All right, so again, my class note that if it's in red, that goes into your dictionary. So pause the video and write down the definition for an orbital in your dictionary. It's a very common definition on the exam. So pause the video and do that now. Now, what's important to note here is that electrons can hold up to 2 electrons. Sorry, orbitals can hold up to 2 electrons. All orbitals, no matter what type, what shape, they can hold up to 2 electrons. Okay, that's really important. Orbitals hold 2 electrons. One type of orbital is spherical in shape. So if we were to use this here, this is a 3D axis. So you've got your X and Y axis. We've also got the Z axis. And Z axis goes out of the page towards you, or out of the screen towards you, and the back of it goes into the screen away from you. So it kind of shows 3D. And essentially what we were drawing here is if the nucleus here is in the middle, then one orbital would be a spherical shape around the nucleus. Okay, kind of hard to draw in 3D, but it's a spherical shape around the nucleus. It's going in 3 directions. It's kind of like a ball, if you want to imagine, a ball around the nucleus. Okay, This type of orbital, it's a spherical shape, is called an s orbital. S orbital. And s orbitals can always hold 2 electrons, as can all orbitals. Doesn't matter what shape, what type of orbital they are, always can hold 2 electrons. So I can put 2 electrons into that sphere. Okay, so these are known as s orbitals. One of these s orbitals makes up the sublevel of each main energy level. So you remember when we talked about before, if we look at the different energy levels, we have the n equals 1, we had n equals 2, we had n equals 3, and so on. We remember that n equal to 1 was made of a 1s sublevel. Well, that 1s sublevel can hold 2 electrons, and that's just an s orbital. So an s orbital makes up an s sublevel. Okay, so there is also then a 2s sublevel, and that is made of another s orbital. So where would that be up here? Well, I'm going to draw in red. That would be like a spherical region that's a bit further out than the black one. It's a bit further away from the nucleus, but it's also a spherical shaped orbital. The n equals to 3 can also have an s sublevel, 3s, and it's made of another s orbital. So this is another spherical shape, and it's further out from the nucleus. So don't mix it up. This is starting to look like a Bohr atom, but we're just drawing s orbitals here. And all of these 3 orbitals can hold 2 electrons. Okay, 2 electrons can fit in here. All right, that's one type of orbital. Okay, so there is another type of orbital that we need to know, and these are what p sublevels are made up of. So p sublevels are made up of 3p orbitals, okay, and all of them are equal in energy, and they have what we call a dumbbell shape. So what does this look like? Well, obviously, the n equal to 1 energy level has no p sublevel. It doesn't have one. It's only got a 1s. We learned that already. But the 2, n equal to 2 energy level, that does have a 2p sublevel. So, and this is why we drew it as 3 dashed lines the last time, 2p. And we said it could hold 6 electrons. And that's because it's made up of 3 orbitals. And each of the orbitals can hold 2 electrons. So that's why there's 3 dashes here, and it can hold 6 electrons. So how do we draw that? Well, we say they've got a dumbbell shape. So in the middle here, we've got the nucleus in black. And around this, arranged in 3D, are these 3p sublevels, and there's 3 of them. Now, a dumbbell shape kind of looks like a figure of 8. We would draw it like that. And that would be a dumbbell. Dumbbell, kind of like the weights that you lift. That's a dumbbell shape. All right. So the idea here is that in the second energy level, or the 2p, n equal to 2 energy level, there is a 2s, but there is also a 2p sublevel. And the 2p sublevel is made up of this p orbital, and this is known as the 2px orbital. Okay. We also have one that goes upwards on the y-axis. There's another dumbbell. So we'll draw that like this. This is the 2py. And then we also have one, and this one's hard to figure out, but it's going on the z-axis. It looks a bit messy there now, but hopefully you can see what I mean. So this one's going sideways, diagonally, and this is the pz orbital, or in this case, we're talking about the second energy level. We might not always write the numbers because there'll also be a 3px, a 3py, and a 3pz, but that's generally the shape of them. So there are, in a p sublevel is made up of 3 orbitals: the px orbital, the py orbital, and the pz orbital. And each of these can hold 2 electrons. So we've got one here, one here, one here, one here, one here, and one here. This is why a p sublevel in total can hold 6 electrons, like that. So if we take the n equals 2 energy level again, reminder, this is how it works. We've got the 1s, and because that's the spherical shape, it can hold 2 electrons. And then we've also got the 2p, which is made of these 3 orbitals. px, py, and pz, and that can hold a total of 6 electrons. So 6 electrons, and this is 2 electrons, a total of 8. And this is why we always said the second shell can hold 8 electrons in a Bohr model, if you like. All right, so let's go back to the booklet here and look at the shapes. So here you can see, so let's just go back here. This is where we were. So we got the px, py, and pz. These are arranged in 3 dimensions along the x, y, and z axis. And so they are called the px, py, and pz orbitals. Because of this, we say that a sublevel is a subdivision of a main energy level that is made of 1 or more orbitals of the same energy. So that's what a sublevel is. It's a subdivision of a main energy level, and it's always made of 1 or more orbitals of the same energy. So all these 3 had the same energy. They all belong to the same sublevel. All right, so again, there's another bit in red there, the definition of a sublevel. So pause the video and write that down. Sorry, my screen's gone AWOL there. Where are we at? Sorry, have to find it again. Apologies about this now. Come on, right. There we go. All right, so in red, you've got to pause the video and take that down into your dictionary. The second one, what a sublevel is. Okay, so here we see the shapes. That's the s orbital arranged in 3D around the x, y, and z axis. So that's a bit better than my drawing. You can see a bit more 3D. There's always one orbital in an s sublevel. It's a spherical shape, so we describe it as a sphere. It can hold 2 electrons. So the total number of electrons in that sublevel is 2 because there's only one s orbital. Here's the p, and again, you can see them organized around the nucleus. Oh, Jesus. Sorry. There we go. There's the p sublevel here. A p sublevel is made of these 3 orbitals, px, py, pz. That's how we would draw them out one by one. You do need to know how to draw them. There are 3 orbitals here altogether. They are dumbbell shaped. Each orbital can hold 2 electrons. So there are 3 orbitals holding 2 electrons. That gives you 6 in total for the sublevel. The D, we don't need to know anything about the shape. The D sublevel is made of 5 orbitals, but we don't need to know their shape. Each one can still hold 2. Any orbital is always 2 electrons to give you a total of 10 in a D sublevel. All right. So we're going to answer these questions now about orbitals. So pause the video now and answer those questions. And my group, we will correct them the next day in class. Okay. Sorry, there's a couple of mistakes here. I'll just fix them before we go. That one should say 254 and that one should say 256. Okay. All right. So I'll see you the next day. Thanks, guys.